Okay, so it's a pleasure to introduce Sahana Vasudevan from MIT. She'll talk about large unit geometry of triangulated surfaces.
Thanks for the introduction and thank you for the invitation to speak. So let me start by defining what I mean by triangle. We take equilateral triangles. And we glue them combinatorially to form a genus surface. And if you get a combinatorial genus surface, then each equilateral triangle you can view as being embedded in the complex plane. And so you have a complex structure on each triangle, which is preserved by gluing and extends over the vertices. So you actually get very much.
Why does it extend over the vertices?
By multiple Riemann and multiple singularity theorems.
I just wanted you to explain it. I think it's a miracle.
Oh,
that's okay.
okay. Yeah, okay. So yeah, so I said large genus here. And so that means I will assume that in particular will be greater than 2 for the rest of this talk. And also, if you have T equilateral triangles gluing to form a genus surface, for the combinatorics of that to work out, you need to have T to be at least T. So we'll also see.
Sorry, I don't understand what you said. So T is an equilateral triangle.
It's a number.
T is
it's a number.
It's a number of equilateral triangles. You can
Okay.
Yeah, okay, great. So I just want to mention that since we're talking about these Riemann surfaces of genus at least 2, we have the following equivalence. On one hand, we have compact complex line manifolds, and we also have compact oriented hyperbolic surfaces, and smooth projective algebraic curves. And these are all equivalent. In particular, I define triangulated surfaces as being in here, but each one comes with a unique hyperbolic metric. And so for the rest of the stuff, we'll just speak of the hyperbolic metric. So unique conformal hyperbolic metric. We'll speak of the hyperbolic metric associated.
On the third one, you really should say the complex structure that comes from projected algebraic curves, because there are more ways to present the complex structure as algebraic curves, possibly different degrees.
Sure. There are many embeddings into projected space.
So it's as complex as Riemann surfaces.
Right.
Okay.
Yeah. Okay. So given this context, I want to start by asking the following question, which is, and I'll write it a bit imprecisely first. I will explain what it means. What is the large genus geometry of a random triangulated surface? Let me explain what I mean by this. Okay, so geometry is going to be with respect to the hyperbolic metric. So we're interested in looking at various geometric quantities, for instance, like diameter. Randomness is going to be uniformity. So they're given a particular T and a particular G. There are a finite number of T triangulated genus G surfaces, which leads to what does large genus mean? So in particular, this means what happens when T goes to infinity, and if G goes to infinity, since T is at least G also goes to infinity. And since there are two parameters here, if you don't want to think about two parameters, an interesting thing you can do is simply set T to be around theta G for theta constant. And theta has to be at least 4 for the combinatorials to work out. And then basically you're asking the question, so moduli space, I mean, you have like the genus is increasing, so you have different moduli spaces. And then for each one, you have a bunch of triangulated surfaces. And yeah, you want to understand geometric quantities. Okay.
What does uniformly mean?
There are a finite number. This is, yeah, you just pick one. Uniformly.
So you're randomly gluing the triangles to each other?
Yeah. So I mean, you yeah, if you want to be very precise, you can the gluing scheme is given by a triangular graph with some extra structure, so you can sample over that. Any other questions?
I mean, you glue in all possible ways in this discussion.
Yes. That the gluing scheme is given by a triangular graph with some extra structure orientation.
But the gluing scheme is not part of the, you take all gluing schemes that are possible, right?
Yes, but that's given by the triangulation graph. Like
Yeah, well, sure, that's what a triangulation is.
Yeah.
Okay, fine.
Sorry, if you have theta G triangles, what is the probability of getting a genus G surface?
yes, I'm so two things. First, when I ask this question, I'm conditioning that I get a genus G surface. Second, if you just have theta G surface, triangles, and you glue them, and you ask, the expected genus is going to be around theta G over 4. So if you don't condition, most of them will be around T over 4 genus. Yeah.
And that's what I wanted to ask you. So this is not really an unnatural, you haven't changed the effective probabilistic structure, because the random triangulation will sort of behave like this.
Yeah.
And therefore you're allowed to consider it for these questions.
Yeah.
Okay, fine.
Yeah.
Does theta matter beyond the fact that it's bigger than 4?
Sorry, I didn't get.
Does theta matter beyond the fact that it's bigger than 4?
No, I mean, so this is just a heuristic that you can keep in mind.
Okay.
Like, yeah.
It's not 2 parameters, it's kind of 1 parameter.
Yeah. Okay.
Could we expect a connected surface if we do a random gluing?
The condition that everything is connected.
Okay, but if we allow disconnected surfaces, would they dominate if we do a random gluing? Or
That's an interesting question. I don't know the answer.
I mean, because if they are minorities and it's irrelevant.
I mean, so like the way I'm doing the gluing, like if I take gluings to be sampled by trivalent graphs, I'm going to get a connected surface. So I'm not even considering that question. Okay. So Brooks and Makover studied this question. And they studied this question when theta is around 4. And yeah, so they got the following results. So the probability that the systole, which is the length of the shortest non-contractible on the surface. So the probability that the system is at least constant tends to 1 in the large genus limit. This is for a specific constant. We found a constant surface, not for all constants. The probability that the diameter is at most around log g, that also tends to 1 in the large genus limit. And then finally, the probability that the Cheever constant is greater than C, this also tends to 1. So I'm not going to explain what the Cheever constant is, but intuitively, it basically measures how difficult it is to cut the surface in 2 pieces of roughly equal area. So if you want to cut a surface into 2 pieces, you require some curve to do that, and that curve has a length, and how much length do you need to do that? And basically, if I parse this, what this is saying is that a random triangulated surface is quite difficult to cut. So it looks like an expanded Gauss.
So in the Cheever constant, you normalize by the genus squared or something?
Yeah.
Genus squared, right?
Yeah, so the Cheever constant has a normalization problem. So another way to think is first eigenvalue of the Laplacian. Yeah. Okay. So now let me ask a related question. By the way, if you try to imagine the surface with the properties that I wrote down there, like diameter around log g, and Cheever constant greater than C, it's quite difficult to do so because such surfaces don't embed very nicely in R3. Very isometric. So the second question is, what's the large genus geometry hyperbolic surface? Okay, so again, same conditions about G apply, G goes to infinity. But now, and geometry means the same thing. But now, what randomness means is more complicated because you don't have a discrete set anymore. So what does randomness mean? So moduli space MG is it parameterizes this T Riemann surfaces or hyperbolic surfaces, they're all the same. Like that. And this is actually this has a complex structure. It's nice dimensional, and it has a Taylor form on it. And that's called the associated volume form. It's called the Bay-Peterson volume form, which I'm not going to define because I actually don't need it for the rest of the talk. But it's some geometrically natural volume form that you sample with respect to. So randomness is with respect to that, and then you ask the same question.
So you use that one because it's not complete, so you can get a finite volume. For the whole
Yeah,
space.
yeah, sure. Yeah, so the Bay-Peterson, well, okay, so the Bay-Peterson metric is not complete. Yeah, so the Bay-Peterson volume form on moduli space, if I integrate it, it's fine.
Right, but because of that top line up there, you're randomly going to be in a compact set anyway. So any volume would work.
No,
This
no.
system is bounded from above.
So this is a separate question from that. It's just a related question.
There's a consequence. All things are related.
Oh, okay.
There's a consequence. Mumford's compactness theorem. If there are no short curves, that's a compact set. So randomly, we have that property, the probability of 1. So therefore, it doesn't really matter to discuss the finiteness. I mean, it's a consequence of
It depends
random.
what question, what geometric quantity you want to
Yeah.
understand.
Maybe I should, yeah. Okay.
Her point is that she's asking.
Oh, I see. This is
collection-
about special cases.
Yes,
Oh, I see.
or particular quantities, particular geometric quantities.
No, but that quantity forces you to be in a compact part of modulus.
Sure, but she might not be looking at that quantity.
Yeah, okay. So I think this
That's
gets cleared on
probability
one
1,
side.
that quantity. But not making a point, there's a math point, that has probability 1. So that means the measure is living in a compact part of the modulus space. That's what I'm saying. But those are not all the hyperbolic metrics, those are the ones constructed in this way, so my comment has less relevance until you prove something else. Okay, sorry.
Okay, so Mirzakhani sent me this question. And he got very similar results to Brooks and Makover, except so the system is just a bit different. So the diameter is around log d. It's probably 1. The super constant also is similar to that, but the system this is only true for this
Oh.
is strictly positive, but it doesn't tend to 1 because the main Peterson volume of within so so the part of moduli space where you have a surface with a short geodesic, that's called the thin part of moduli space. And the Bay-Peterson volume of this is a constant proportion of the total Bay-Peterson volume of the moduli space as people say. So
Okay.
you don't get the same result for here, but for these two, you do get the same result.
Okay, thank you. So, yeah, that's what Laura was.
Okay. Yeah, any other questions? Okay, great. But like if you just ignore this for a moment and you just look at the complement of this, which is called the thick part of moduli space, then you do very much have a similarity between this and that. And this similarity is actually echoed in many other results by other people that I won't list all of them. But that sort of motivates us to ask our next question. The question 3 is our triangulated surfaces with key triangles. How are they distributed in moduli space in the large genus limit? Quantitatively. Okay, so this is a bit imprecisely worded. So let me say how I'm going to make it precise. But actually, before that, so basically, Brooks and Makover were the first people to start asking the question of how T triangulated surfaces are distributed in moduli space, and then Mirzakhani proved this, and then there were many other results describing the similarity, and so more people started asking this question. By the way, if you forget about the word quantitatively for a moment, so maybe I'll just mention it aside. theorem says that triangulated surfaces are exactly algebraic curves defined over 2 bar and 2 bars dense in C. So this, like if you forget about conditions on T for a moment, just take all the T. This is dense in modular space, topologically speaking. Yeah. But we're interested in quantitative versions. So what do I mean by quantitatively? So I'm going to put a metric on modular space, and then I'm going to look at a ball in that metric, and then I'm going to ask.
Some of us here don't know Bayes theorems.
Sorry.
Some of us here don't know Bayes.
Yes, so that's fine. I mean, it's just an aside. So like it's just an aside for people who do know that. I won't be using this later. Yeah. But you can think of this. This is like almost the content of Bayes theorem. It's usually phrased differently. Yeah. Okay. Yeah. So what we're going to do is put a metric on moduli space, and then look at a ball in moduli space and think about how many key triangulated surfaces fall in that ball. So what metric am I going to put on moduli space?
Just a quick question.
Yeah.
How often do you expect that Riemann surface will make 2 or more equilateral triangulation? Does that happen?
So do you mean that in a quantitative sense or in an absolute sense?
Quantitative is fine. Whatever.
Yeah, it's going to happen like a lot, probably.
Okay.
Okay. Yeah, so to put a metric on modular space, what we need to do is understand so what it means for 2 Riemann surfaces to be close, or what is the distance between them. So for that, I'm going to define quasi-conformal distance. So a map x from x to y is called quasi-conformal. If I'll sort of explain intuitively what happens. So on the tangent space of x at each point, you have you can choose an orthonormal basis such that these 2 vectors get mapped to, I don't know, something like this. And being quasi-conformal means that, yeah, so the ratio here should be close to 1. Yeah. Between k and k inverse. So in this case, k is greater than 1. 1 quasi-conformal means it's conformal. So in a conformal map, like infinitesimal circles will get sent to infinitesimal circles, but in a quasi-conformal map, they will get sent to ellipse. And I think this ratio is called the eccentricity or something. So that is what k is. And then the time polar metric on moduli space okay, so the time polar metric is defined as follows. You simply take all quasi-conformal maps and then you take the int to the log, so that just becomes a metric, and that half is well, it's exponential. So So let me just anticipate a few questions. So earlier we were talking about the Wade-Peterson measure, which I didn't define. And someone might ask, well, why aren't we using the Wade-Peterson measure comes from a Taylor structure, so it comes from a metric called the Wade-Peterson metric. Why we're not using that metric is because it's not complete. And it's really hard to understand the large genus geometry of the Wade-Peterson metric. And then the second point I want to make is that since we have these kind of similarities between the geometry over there and here, the tripolar metric actually measures how the geometry of the hyperbolic metric changes. So for instance, if you have k quasi-conformal maps, then you can look at how much the diameter Cheeger constant change in the hyperbolic metric, and it will be something k to the something. This is not trivial, but it's true. So it is the kind of natural metric to look at, a natural metric to look at. Any questions? Okay, so we're now going to answer question 3. Triangulated surfaces in a one ball, so this just means radius 1 ball in the triangular metric. So here, C is a constant that is independent of everything. It's like 100 or something, or maybe more than that. Just like all of those constants were also supposed to be independent of D and P and everything. Yeah.
When you do the counting, do you count the multiplicity if they correspond to the same genus surface?
I mean, yes. Yeah, so triangulated surfaces are a combinatorial object.
Okay.
Yeah, so if, that's the point of the theory. So like you have, this is a combinatorial object, and this is a kind of geometric object.
Does C depend on G?
No, C doesn't depend on anything. C is like, maybe it's like, I don't know, like some very large number, but it doesn't depend on it. No constants in this talk will depend on anything they're not specified to be dependent. Yeah. Any other questions? Let me give some context to this theorem. So the number of balls, balls, cover the thick part of moduli space is around G to the 2G. This is by Spector, Kahn, and Markovich. Yeah. Also, the number of triangulated surfaces. This is around C to the T times G to the 2T. This is by Rodzinski and Brook. By the way, this is true in the range where this question makes sense. So this is true for like T greater than a constant times 4T or something. If T is very small, then this number will be 0. But this combinatorial problem of trying to count how many T triangulated genus T surfaces there are is actually quite a difficult problem. And so this actually isn't an asymptotic. So their bound is better than this. They have an exponent, but just so. Okay, so the picture is as follows. So MG looks like this. There are a bunch of balls. This is the thick part of MG.
Let's see. This statement is under this yellow assumption, or this yellow fact.
Yeah.
Fact of life. T and G go together.
Yeah, but I just want to say that this statement is true on the nose. Like this doesn't. I mean, you just any T you have, any G you have this. Okay. Yeah. So there are about these are the 2D balls. You can cover this bit, and then there are this many triangulated surfaces. Some sort of well-distribution result you would expect, around C to the T in every ball. That's the theorem. Okay.
So you're saying that your result is like a local version. It's like you fix a ball, but they took all the balls. Is that what you're telling us?
Yeah. So they're taking all the they're counting. Yeah, by this is a combinatorial question, but what I'm asking is what happens if you also fix the conformal class and look near that particular conformal class? So yes, it's a local. By the way, since you mentioned that, the number of T triangulations of a sphere, which is a genus zero surface, this is around C to the T. So of course, this is the combinatorial statement. Sphere has only one conformal structure. Of course, if you increase the genus and you want your constants to be independent of everything, you're going to have way more triangulations. But what my theorem is saying is that if you, just like here, there's only one conformal class, if you restrict the conformal class, then you get back this bound. So it's kind of a genus independent bound in that sense. Yeah. Any other questions? Okay. I'm also wondering to the organizers, when do I end? Or
Maybe you should take a little more time because they said it's 10 minutes late, so. Be 11:05.
okay, sounds good.
So you can, Dora, I think alluded to, you could probably prove this Kahn, Markovich, Fletcher result from your result, right?
Yes, that's true. Mhm.
Put the two together.
Yeah, this and that together. Yeah. But this was proved much earlier.
Yeah.
Actually, by the way, the way this was proved is by considering like a subset of triangulations, not all triangulations, but yeah, so
This is the thing with the pair of hands that were twisted to then glued.
Yes.
Yeah.
I mean, those guys used to be here. The last two used to be here. I think we heard some of this story.
oh I see. Yes,
So we
they
heard
have
a lot of
many-
this story as it happened.
Okay. Yeah. Yeah, so I guess another thing to just think about that I won't write down is that maybe like it's a bit difficult to imagine what well distribution means in the sense because in a large genus sense you have the spaces that themselves are changing. So a good mental model to have is like what integers look like in Euclidean space. And if you look at a volume 1 ball in a high dimensional Euclidean space, then it has around C to the dimension number of lattice points. But that exponent kind of changes as you vary the ball. It's like very unstable. So that's kind of this bound. And maybe that's a reason that maybe you here you cannot expect another bound. Okay. So in the remaining 20 minutes or so, I'm going to explain first, kind of, what is the difficulty behind answering, proving a well distribution result of this type, and then how that obstruction is resolved.
Do you have an image of what a random guy looks like?
Sorry,
Do you have an image of what a random guy looks like?
random what?
Surface.
Oh, yeah. So as I said earlier, a random surface is a bit hard to imagine because it has very small diameter. The diameter is like logarithm of the genus, and it's also like very difficult to cut the surface in half. So I mean, such surfaces do not sort of embed in Euclidean space or embed in R3 in a sort of isometric manner. So it's hard to have an image, like because images are usually thought of as,
So it sort of stands out like a tree.
Yeah, I mean, a good, maybe one way is to think about intuition, like surfaces are like graphs. So like maybe expander graph would be like an image that it can have. Yeah.
But I remember trying to make a small diameter for large genus. You have to take a big disk and put little things around the boundary. So there's like a picture, there's a big disk
I see.
inside, but that's not, I don't know if that's high probability or not, but it fits with that log G estimate, that's the probability one. If you try to make something that short, that's a lot shorter than a genus, a log G, right?
Yeah.
So then you have to make a big thing, and the area is genus, proportional to genus, right?
Yeah.
So you have the diameters, so you have to sort of, it's like, that's a hyperbolic ball, area G has radius log G, a hyperbolic disk. So a big disk inside a random surface or not?
Oh, okay. So
I mean-
yeah. So I think it's yeah. Like I mean probably. So yeah. Like that's. So that's all I can say. Probably, but
Since
it's
it's
hard
a
to make that
probabilistic
statement.
statement, that
Yeah.
means yes.
So I guess.
Okay, so it looks like a big piece of it.
Yeah. By the way, so if you
That's
so if you want to imagine the hyperbolic metric, it's easier to do so when the number of triangles is close to 4D, because in that case, the number of vertices will be very small. It will be like log G. So you will have very few vertices or very high degree. And then when you look at the hyperbolic metric on such a surface, those kind of vertices will turn into kind of big disks. So yeah.
What's the combinatorial picture you just
Yeah.
described? I didn't get it.
Yeah, I can write something down. So you look at 4D. P is about 40 slightly bigger than 4D. Number of vertices. What's the Makover study? The number of vertices is very small. It's like log G. So it's like 4D plus log G or something. And yeah, so you have like the flat metric looks like this, where each of these are supposed to be equilateral triangles. But when you put the hyperbolic metric on it, this becomes like a disk. Yeah. Okay, so let me explain the difficulty in question 3, which I raised, but this is about asking how are triangulated surfaces distributed in moduli space. So it's the following. Given two particular triangulated surfaces, suppose you want to answer the question, are they close in moduli space? So I have two particular triangulated surfaces, which are combinatorial objects, and maybe I want an algorithm to say whether they're close in moduli.
Close means order 1 or something.
Yes.
Close means order 1.
Yeah, so like close, I mean, yeah, so I mean within, so I mean, C quadratic.
Yeah.
Yeah, okay. So this is hard. I mean, I still don't know how to do this. And in particular, you can think about it. So there are two different worlds. One world is the world of triangulated surfaces, which is a combinatorial world. And the other world is the world of hyperbolic surfaces. And it's relatively easier to check if two triangulated surfaces are combinatorially the same. That's like checking whether two graphs are isomorphic. But how do you check if two surfaces, hyperbolic surfaces, unmarked? Sorry. Yeah, two marked hyperbolic surfaces are the same in moduli space. That you have to kind of go through all the elements of the mapping class group, and that's fine.
Yes.
Okay. So how do we get over? Yeah. Any other?
You're asking in moduli space, not in type of.
Yeah, not in hyperbolic.
So to go through the market.
Yeah. So yeah. Any other questions? Okay. So let me explain how to, in the rest of the talk, I will try to explain that key idea in the proof. That will hopefully explain how we get past this particular abstraction. So basically, the point is that you can prove this theorem without being able to answer that question. Okay. So for that, I have to explain something, which is what is a translation surface. So translation surface, there are two definitions that are equivalent. One is you simply have a polygon in the plane or a collection of polygons, and you identify parallel opposite edges together. So maybe these are identified, and you do gluings here. And by the way, if you do these gluings, you will probably get a genus 2 surface. Okay, you can have more polygons and identify them. But since the gluings are of parallel edges, the gluings are by translation. That's why it's called a translation surface. And now, if you look at this picture, since this polygon is considered as embedded in the complex plane, there is this differential form dz, differential one form, that is preserved by the gluing. So this isn't just a Riemann surface, but it also comes with this. Which leads us to the second definition of a translation surface. It's a pair x omega, where x is a Riemann surface. And omega is a holomorphic one form on it. Let me just explain what is a holomorphic one form. So it's something that locally looks like f of y dy for holomorphic coordinate y, and x is holomorphic. But any form like this, locally you can change coordinates so that this form becomes dz.
Only
Where it's not zero.
Yes, away from the zeros, sorry. Yeah, away from the zeros, you can do this.
Better compound.
Yeah.
Otherwise, everything's a force.
Yeah. Yeah, thanks. So actually, now if you look at dz, that's kind of like, you can imagine that a dz on the complex plane. So what you actually get from a holomorphic one form is you get a flat metric from the zeros. So the zeros, you get a flat metric with singularities. Okay. So here the zeros, this will be good, where the zeros. Okay. So this leads us to the following. Basically, the point is that if you have a holomorphic one form, you get a flat metric with singularity. I'll sometimes omit the word singularity. What about the opposite? So if you have a flat metric with singularities on a Riemann surface, it doesn't mean that it comes from a holomorphic one form. For instance, triangulated surface gives you a canonical flat metric, just coming from the Euclidean structure on each of the unit equilateral triangles. But it need not come from a holomorphic one form. You can have like 4 equilateral triangles glued. These are equilateral triangles glued at a point. That doesn't come from a holomorphic one.
But it comes from a square.
It comes from a 6 differential. It like locally it will something look like easy to the 6.
Really don't have a quadratic differential.
Because the angles are 60.
Yeah.
So that
Okay. So what we're going to do is just simply, for a moment, consider the triangulations that do come from holomorphic one form. So I'm going to call by combinatorial translation surface triangulated surfaces that are also translation surfaces. In a compatible sense. Means that the metric, flat metric coming from the translation surface is simply the same as the flat metric of the triangulated surface. So this is a combinatorial condition on the gluing basically.
Does it mean that you can put the triangles into a polygon? Is that what you're saying?
Yeah, it kind of, yeah, the fact that you can identify each triangle with one on the complex plane and then gluing will be triangulation. That just reduces the combinatorial.
Are there other obstructions of being a combinatorial translation surface other than the vertices?
Yeah.
The degree of the vertices?
Yeah. Okay. So now if let's consider the following thing. So suppose S is a combinatorial translation surface. And X is its associated Riemann surface. Then I have from the translation structure a holomorphic one form on X, and this holomorphic one form actually detects the triangulation. I can rebuild this gives me a flat metric. Starting from the singularities, I can rebuild the triangulation. And yeah, so if I know PS, I know the triangulation. Okay. Now, what is also true is that this belongs to a certain cohomology class because it's a holomorphic one form. So the first idea is instead of counting surfaces, we're going to count cohomology classes.
you're going to count surfaces in a cohomology class? What do you mean? You're going to count cohomology classes?
Yeah, we're going to do everything. We're going to count cohomology classes when we count surfaces that in a particular cohomology class also. Okay. Yeah. So let me just explain a little bit of forms, these are complex valued by exact one form. And the Hodge decomposition actually gives closed forms, closed complex value one forms, as harmonic forms plus exact forms, and these are orthogonal with respect to the Hodge inner product and Hodge norm. So in just a few moments, I just want to explain the next idea. Okay. So the difficulty I said was that you have triangulated surface R and S, and you might hit moduli space X and Y, and you don't know, you cannot say that because X and Y are close, then R and S are almost the same triangulation. That's the difficulty that I explained. But if R and S are actually combinatorial translation surfaces, then I can do the following thing. Since X and Y are close in moduli space, I have a quasi-conformal map between them. And assuming these are combinatorial translation surfaces, I have a holomorphic one form of X and Y, and I can take the pullback, which is a one form on X, but not necessarily holomorphic. And now I'm going to look at the cohomology of X. And now I'm going to assume this additional condition. So this lies in the cohomology, but this also has a particular cohomology class because it's a closed form. And now I'm going to look at what happens if these two cohomology classes are close to each other. So cohomology classes being close means that so because of the Hodge decomposition theorem, the harmonic part of this, which I'll denote by this, this means that the cohomology classes are close. And now I use the following trick. I claim that I can simply remove this H. So why is that true? That's true because of the following trick. So I can rewrite this as okay. Now this is exact because I'm subtracting a harmonic form from its harmonic part from this part, and this is harmonic. So these are these are orthogonal, and so this is simply and because F is C quasi-conformal, this is actually very close to this, which are both very close to the Hodge norm of TS in Y. And therefore, this is actually small. And what that means is that actually we can remove this. And so from a condition about cohomology process being close, we get a condition about the one forms associated to the triangulations themselves being close in this sense. And from that, we can get a combinatorial condition about the triangulations being close, since the one forms detect the triangulation.
Why isn't that 0? Those are exact forms. Stokes theorem tell you that that's a 0?
This is the Hodge norm on, not on cohomology, on complex valued one forms. Yeah.
What's the norm? Sorry.
Oh, okay. Yes, I didn't write that down because
The L2 norm.
yeah.
If it's the L2 norm, that should be 0.
No. It's the integrated positive thing.
Okay, I'll
You
stop.
don't integrate a sign.
Oh, it's not the wedge product. With the
No, it's wedge star.
Okay.
Okay, yeah. So the point is that I couldn't say that arbitrary triangulated surfaces, if they're close in moduli space, then their triangulations are close. But if they're also combinatorial translation surfaces and their one forms are close in cohomology, then I can make such a statement. So that's how we get around.
No, but what's the state?
Yeah.
I mean, I followed it locally, but I don't have the overall statement. Well, can you just repeat this?
Yeah.
Don't write it, just say it word.
Yeah. So basically, the statement is if R and S are combinatorial translation surfaces, and their associated one forms are close, and they hit surfaces that are close in moduli space, and their associated one forms are close in cohomology, then the triangulations coming from them must be close on most of the surfaces. They must be the same triangulation on most of the surfaces. That's the statement.
Thank you.
So that's how we get around the difficulty. And then we can actually remove these conditions.
This is like candy.
Are there any questions for Sahana? Yeah. So you had an upper bound, and maybe this is a dumb question, but can you get a lower bound at all?
Yeah. Yeah. So I also get a lower bound that's also exponential.
Okay.
And the exponents are different. But you should maybe expect that because that's also the kind of the case in this. That's why I gave this model of integers in Euclidean space.
Can you ask similar questions for square child surfaces?
Yeah, I mean, well, square child surfaces are actually translation surfaces. So these arguments should just go through.
Okay.
Yeah.
What about vector ones?
Yeah, so I mean, so anything that's not a translation surface, so I didn't explain the part of the argument that involves removing these extra conditions that I added. And I don't want to make a statement that everything works before actually checking that everything works. So you could probably use the methods to say something.
What is the proportion of combinatorial translation surfaces?
Yeah, that's
For
what
all
that's
triangulated
the part arguments. Like how knowing this information about these surfaces, how does it give you information about all the triangular surfaces?
Yeah, so that's a part that I didn't explain. I can explain that now. What? So basically, if you have a combinatorial translation, so the question is, how do you now have some result about combinatorial translation surface? How do I extend it to arbitrary translation? So now, if I have an arbitrary triangulated surface, as you said before, it gives me not a holomorphic one form, but a holomorphic 6 differential. And if I pass to a 6-degree branch cover, then it gives me a holomorphic one form. So that's what I do. Instead of counting triangulated surfaces, I count translation surfaces on a higher dimensional modulus. I mean, of course, when you do this process and try to make all of this work, you have to kind of control where the branch points are, so the branch cover, so there's some work involved, but this is the argument.
So it's not a modulus, it's a cover of the.
Well, the
It's
surface.
the surface is a branch cover, so you have a canonical, if you have a triangulated surface, you have a canonical 6-degree branch cover, which is a combinatorial translation surface.
But you said something about on a higher dimensional modulus.
Yes, so why higher dimensional moduluses? Because your canonical branch cover will have a higher genus.
Oh, I see.
Yeah.
Any other questions for Sahana? Not, let's thank Sahana.
The reference? Is there a reference?
A reference meaning.
Did you write up your?
Yes,
your
it is
paper?
on the archive.
I mean,
It's
on
called,
on the lecture, I mean, or on the material, on the lecture.
yes, so this is based on a paper, which is on archive, which is called Large Genus Bounds for the Distribution of Triangulated Surfaces in One Surface.
You guys should email.
Oh, okay, yeah, sorry.
I think Chris actually sent it out.